Hi, everyone, and welcome to the hands-on part of decision trees. It's going to work the same way as we were when we were working with k-nearest neighbors, in that the first thing we do is create a classifier. So that's that first line, CLF equals. The next is we're going to train that classifier on our training data. So we're going to give it a set of features and their associated labels, and that classifier, that decision tree, will learn the relationship between those features and the labels. We'll come up with those rules and the ordering of those rules that'll help us make predictions. Finally, once the classifier is fit, once it's trained, we can use it to make predictions. So as we talked about before, this is called supervised learning, right? So in supervised learning, we make a classifier, and it's kind of an empty shell of a classifier. It really doesn't know anything until we give it some training data. So we give it some labeled data, meaning there's a set of features, and for each feature, for each row of the table, for each entity, we have a label associated with it. So the one example was the dogs and cats. There could be many others, but we have features and then the label that we're trying to learn. And after that, then we have the trained classifier. The classifier has now learned some relationship between those features and those labels. Once we have that done, we can throw away the training data. Now we have this trained classifier that we can then use in whatever application we want. So we can develop some web-based application, we can do some phone-based application, we can use it in whatever mode we want. We have this trained classifier. And that trained classifier is going to take some data to be classified, so it's unlabeled. We want to know about, well, is this a dog or a cat, or segment stuff, and it's going to assign some label to it. So that's what supervised learning is. There was an interesting article I read just recently about data and democracy by this person. He has a book called Data and Democracy and gives kind of machine learning ideas related to democracy. And one thing that came up then in thinking about this is that decision trees are used a lot for demographic data. So if you have a lot of demographic data and you're trying to do some classification on it, decision trees aren't a very bad way to go. One thing to look at is what's called modeling and micro-targeting. So you want to maybe, instead of just doing a mass mailing for political purposes, is really target specific types of people for a specific type of mailing. And for that, this is from that article or from that book, where you have this likelihood of voting here on the left side. So whether they're definitely going to vote or they're kind of on the border, whether they'll vote or not. So that's one thing we may want to learn. We may want to classify people on whether they're likely voters. And the other thing might be, well, what's the preference? Is it our candidate that they're likely to vote for, or they're kind of undecided? So based on all those factors, whether they're likely to vote or not and whether they're undecided, may lead us to, have different targeting of ads and things like that. So these are things we may want to predict in making a classifier, what party they are based on some number of features that we got from some demographic data, the likelihood of them voting, are they likely to support the specific candidate that we're interested in, what's their position on a number of issues, are they pro-abortion, pro-guns, or where do they fit in all these issues, are they likely to volunteer or maybe give some donation, and how persuadable are they? So if they're kind of on the fence about who to vote for, can we persuade them to vote for our candidate? And just to go down the rabbit hole a bit more on this and deviate from not quite yet talking about decision trees, is sticking with this idea of using it for voting. And there's been a number of articles. This was one of them, The Good, the Bad, and the Ugly Uses of Machine Learning in Election Campaigns. And I'm sure we all heard of this Cambridge Analytica kind of data breach with Facebook, where they got information on 87 million people. Not a very good thing. But the Cambridge Analytical people were trying to determine what they call personality types, this ocean index of personality, measuring people on openness, conscientiousness, extroversion, agreeableness, and neuroticism. So can we, based on what they do on Facebook, label people with these categories? And it would look like this, that we have different Facebook posts up there and different users, and we're looking at what they like, so what they give a like to, and then we have this ocean label. Originally, their original data set is that they had Facebook people they had some app, I forget the name of it, that gave them, hey, take this app and you'll learn your ocean score, you'll learn your ocean labels. So people did that. So now they had labeled data, right? So they knew what the ocean label was and they knew what people liked, and they were able to combine these into creating, this classification system. But unfortunately, in addition to, taking this information of just the people that use their app, they took the information of everyone that those people liked. That ended up being that 87 million. And this is what one of the people said. These Facebook profiles, especially people's likes, could be correlated across millions of others to produce uncannily accurate results. Michael Kosinski, the center's lead scientist, found that with the knowledge of 150 likes, their model could predict someone's personality better than their spouse. With 300, it understood you better than yourself. Quote, computers see us in a more robust way than we see ourselves, says Kosinski. So it's kind of an interesting use of classification, whether it's good or bad or ugly. So in that system, the Cambridge Analytical system, right, it had some empty classifier. It had this labeled data, so the Facebook users, what their likes and dislikes were, what they liked. And the label part was this ocean score that they got from that little app that people took. And that created a trained classifier. Now they could use that on the 87 million other people to identify who, what the personality type was. And then they could use that for political purposes. So like the Trump administration, I think, and Ted Cruz, or the Trump campaign and Ted Cruz were using this Cambridge Analytical data. Right, so we could see Facebook likes and then label these people. So that's kind of the, thing down the rabbit hole. And now let's kind of, go back up the rabbit hole to get back to decision trees. And before we get started on kind of the details of decision trees, like how to implement them in SKLearn, I just wanted to give one to think about. And this is a made-up example I have from let's say, this is COVID-19 information, people who have the virus, and we're trying to predict whether or not they're going to be put on a ventilator. And this is just some made-up decision tree. So one question, maybe the first one is, do you have a pre-existing pulmonary condition? And then they say no, and there might be a series of other questions. And that final one on the bottom is, what is your BMI, body mass index, greater than 30? So are you obese, in other words? And that's the results down at that node that I forget how many I had. I think eight data points, and 7 of them were yeses, and 1 didn't have to be put on the ventilator. So almost all of them had to be put on the ventilator. So maybe we'd keep developing this decision tree and come up with something like this. So we get real specific here to account for this one single no that we have. So build up the rest of this tree. So it accounts for the training data, but one problem is it might be too specific. So right, it's really tailored very specifically to that training data and may not really be that robust in real life, because that one no may just be an outlier, right? So we don't, there's nothing special about someone who's 32 that won't have to be put on the ventilator, where people above and below the person didn't have to be. So we might want to prune or limit the depth of a tree by doing, just stopping at this BMI is greater than 30 and kind of forget about, or, just consider that an element of noise. So one factor we can do when we're working with decision trees is limit that depth, which I'm not going to talk about in this video, but there'll be more discussion later on. Well, I guess I just did talk about it, but I won't show you how to implement it until the next video. So let's go hands-on. So just a reminder, there is an associated decision tree Python notebook, Jupyter notebook, and it's this one and goes into a fair number of details. So I'm not going to cover that, as I've been telling you all along. I'm just going to kind of go off on a tangent and look at decision trees from just a slightly different way, or a different orientation, a different view. So the first thing I'm going to do is load in some fake data here, and I better do that because I don't think I ran this recently. And it's very similar to that, whether the person's going to mountain bike or not, but it's whether I just wanted numerical data just to keep life easy. and it's whether someone liked a particular camper van or didn't like it. And the factors are wheelbase, how many people does that camper van sleep, does it have air conditioning or not? So 1, it has air conditioning, 0, it doesn't, and whether it has lithium. Right, so lithium battery pack. It's all made up data just to illustrate this. And the next thing I do is I divide it into features, so the features we're trying to use to make a prediction, and then the labels, the thing we're trying to predict. So I'll just do that. And now finally we get to some interesting part, is that we're going to create this decision tree classifier. And the first thing we need to do is import that from SKLearn. And then let's create that classifier. And there's several criteria we can use, and I want to use the one we've been always working with. Okay, so now we have a classifier, and as I said, it's kind of empty, right? It kind of knows, hey, I'm a decision tree classifier, but we haven't trained it. We haven't given it the training data. So now that's what we want to do. We want to fit that training data to the classifier, and it works the same way as what we've seen before. And that was called van features and the van labels. And we've created this classifier. Now the interesting thing is we can actually view that decision tree. So that's a way cool thing we can do. And let's go ahead and do that. And let me back up here. So here is the decision tree. So we say it's all kind of numeric. So even though air conditioner is a binary thing, we go, is it less than or equal to 0.5? So if it doesn't have air conditioning, we go this way. And if it does, we go that way in the false. Okay. So let me explain these things a little bit. So we have here this, I'm going to skip this air right here, but I'm going to talk about entropy, samples, and the value and class. Just kind of explain what that all means in there. And for the samples and value, let me look at that original data here. So here they are. The samples were the 14 examples we have. And let me zoom up. That the value 5.9 means that there were 5, let me go again, 5 no's in our test and 7 yes. 5 no's and 9 yeses. So that's where we get the 5.9. Now, and if we just had to guess what to do, so if there were 9 times the person liked the van and 5 times they didn't, without knowing anything, we'd say they liked it. So that's where we get this class equals like on the bottom. So now I've explained the samples, the value, and the class. Let's zoom up to entropy. How did we get that 0.94? Well, we got that 9.4, let me zoom again, by applying our info, the entropy that we've been using before. All right, so the info of 5.9 is this, 5 over 14 times log 2 of 5 over 14 plus 9 over 14 log 2, 9 over 14. I realize I missed the negative here, just add that in. And if we computed all that out, we'd get 0.94. So there's no mystery there. So we have everything. Let's go back up. So we've talked about entropy, samples, value, and class. Now this error is when we start looking at the columns, right? So we're going to look at all these columns like we did before, compute all those entropy values, and pick the best column that reduces the amount of entropy, or it has the smallest amount of entropy. And the one that did happened to be air. So that's how we got the air category. So the first question is, does it have air conditioning? I zoom up again. And there's all the entries for that. So you can see now the entropy is 0.592. There were 7 of them that did have air conditioning, and those were the values. Right? So it's a fairly intuitive, I'm hoping, that once we work through all the prior videos on, hey, how do these decision trees work, all of a sudden this makes, I'm hoping, a lot of sense of how things work in this SKLearn, that kind of all the mystery, I'm hoping, is gone. So that's all I wanted to really cover here is, how to use this decision tree in SKLearn. It's real easy. Let's back up a bit and just show how that worked again. So here I imported it and just created one using entropy. Here I fit the data. What I didn't do was I don't have any test data. This is all made up stuff. You will when you work through that Python notebook. But the next thing we would do is make some predictions and see how well it worked. So that's it. I hope this was a bit helpful and the political stuff a little entertaining and not disgusting. So take care. See you next time. Bye.